YOLO-V5 is a fast, lightweight, and widely used object detection model. But did you know it's not the official successor to YOLO-V4? And despite that, it still dominates the industry in real-time object detection. I break down deep learning models like this in detail. So if you love architecture deep dives, then you are in the right place. Okay, let's start. This is the first YOLO-V1 paper, and this is YOLO-V2, this is YOLO-V3, and then this is YOLO-V4. And finally, we have version 5. What? No paper? Yes, there is no paper published till date on YOLO-V5. They have only released the implementation in PyTorch, and they have not yet released any paper. Then how is it accepted as a successor to the YOLO-V4 in the research community? Well, there are mixed responses in the community regarding this. So let's go briefly over what exactly happened. It all started with the announcement of YOLO-V5 without any research publication, and all there is a just GitHub repository claiming that it's the best in the whole object detection frameworks. YOLO-V4 got released in April 2020. Within just 40 days or so, a company named Ultralytics released a repository named YOLO-V5 and claimed it's better than all the existing YOLO detection models, both in terms of accuracy and performance. So it claimed that it is giving 140 frames per second, whereas YOLO-V4 gives 50 frames per second. And also the model size is so small that it's only 27 MB, whereas YOLO-V4 is 244 MB. So YOLO-V5 is nearly 90% smaller model and performs on par with the efficient date and YOLO-V4 in terms of accuracy. Is it really true? Well, it's not considered as legal heir to the YOLO family because there is no research publication. But the good thing is they have the repository, so we can just replicate the results and check. That's exactly what people have done. First of all, there are some comments from the LXC, who is the author of YOLO-V4, that the latency should not be measured with higher batch sizes because it depends on the GPU device, and the batch size should always be kept as 1. If multiple batch size is used, then it should be the same for all the models in the comparison. Apart from all these comments, they have trained and tested YOLO-V5 models on the COCO dataset and published the results. The results are a bit controversial here. These numbers show that YOLO-V5 is behind in terms of accuracy. If you see this, these are the accuracy levels for YOLO-V5 and YOLO-V4, and it is almost on par with YOLO-V4 in terms of performance. This particular model is faster, but if you see the accuracy score, it's much smaller than YOLO-V4. So it's not faster than YOLO-V4, and also it's not accurate than YOLO-V4. In fact, the accuracy is lower than YOLO-V4. So the controversy continued for some time before it got subsided. So far, we have seen one side of the controversy, but how did Ultralytics responded to these critics? Glenn Jocher, the founder and CEO of Ultralytics, responded to these comments on GitHub. He mentioned that they don't have the resources for publishing a paper, and he also mentioned that the repository is not complete and it's work in progress. And regarding the naming convention, he said that it's an internal name they have assigned to this project, and if the name is a concern, then they are open to alternatives. If it is an internal name, how can they release it public and say that they are okay to change the name? It's fine. That's all about the controversy. Personally, I feel it's okay not to publish paper because they have made the code available. Several generative AI models came in the last 2 years, right? How many of them are backed by research publications? Even there is no official paper for ChatGPT. There are no papers yet for GPT-4, Turbo, GPT-4o, all the latest models, right? So releasing the models without publication has become the norm. I think it's fine as long as the models are performing as they claim. But the false claims of beating YOLO-V4 is just a marketing gimmick, I feel, and it's not ethical. Yes, they have improved a lot over the years. So it first released in 2020, but then now over the 4 years, they have improved a lot. Even the model architecture they have modified, and now it is much better than YOLO-V4, but claiming back in 2020 is not correct. Nevertheless, YOLO-V5 is considered the go-to repository for most of the object detection tasks. The only exception is its commercial usage. The license is AGPL, which is not for commercial use. So if you want to use it for commercial deployments, you can't do that. You have to contact the people over there. Because of this, many companies restrict the use of Ultralytics. Even I myself interacted with Glenn Jocher as part of my previous company to check about this license and attribution. He's a very nice guy. They have done very good job, definitely. So that's all about the YOLO-V5. Now let's start with the architecture. YOLO-V5 is an object detection model, right? That means it should identify the position as well as the category of the objects present in the scene, right? Now it's time to look at its architecture. Here we go. It's very funny. Wait, this looks like YOLO-V4, isn't it? YOLO-V4 has CSP darknet, YOLO-V4 has spatial pyramid pooling and path aggregation network, and it has YOLO-V3 head. This is exactly same as YOLO-V4. Okay, that should not be the case. YOLO-V5 should be a novel architecture. So let's make some changes. What should we do? Let's start with the backbone. Can we create a new custom backbone? No, we don't have time for that. So let's make a custom filter. Instead of 3 by 3, we will use 6 by 6 filters in the initial convolution layer. Wait, that's it? Okay, let's make one more change. YOLO-V4 uses mesh activation function. We will go with swish activation function. Okay, anything else? Yeah, maybe just add and drop here and there some blocks. That should be good. Yeah, we got a custom backbone now and it's faster. Now let's come to the neck part. YOLO-V4 already uses SPP and path aggregation network. So what should we do? Let's modify SPP to make it as SPPF, faster. Just SPP fast. Then what else? Let's introduce the CSP blocks in the path aggregation network also. YOLO-V4 uses them as part of only the backbone. There is no CSP block in the path aggregation network in case of YOLO-V4. Now we will add that. That will be our custom neck. What about the detection heads? We will also add some modifications here. Let's see that later. Let's call it modified YOLO-V3 head. Okay. So finally we have a custom architecture. What should we name this? YOLO-V5. So it's official. YOLO-V5 is a custom architecture which is very fast and much better than YOLO-V4. Okay. That's how YOLO-V5 evolved from YOLO-V4 as its successor. Now jokes apart, they have done a very good job in implementing the whole thing in PyTorch. Before YOLO-V5, the YOLO series uses darknet repository which is implemented in C language and it's pretty difficult to use or train the model on your custom dataset. So it's not very user friendly. Now with this PyTorch implementation, it has become very easy to use these models for prediction as well as for training on your custom dataset. And also they have been continuously improving the repository over the years. I would say it's one of the best and easy to use repository in the whole object detection world. Even the official repositories like PyTorch or TensorFlow object detection, they are also not so easy to use. It has so many functionalities as well. Let's look at the functionalities. The first thing I want to talk about is the model support. YOLO-V5 supports object detection, classification, and instance segmentation, all three in a single repository. Of course, they released the initial repository for only OD part, object detection part, but then later they added support for classification and segmentation also. Okay. And coming to the training on custom dataset or fine tuning it on your custom dataset, it has many capabilities. It supports multi-scale training, mixed precision training, genetic algorithms for evolving the hyperparameters, experiment tracking with multiple tools like Comet or weights and biases like that, and LR schedulers, auto anchor, exponential moving average for getting best weights for the model. So it supports all of this. As per the data, it supports multiple data augmentation methods such as mosaic, mix-up, and some other augmentation types. And it also integrated with Albumentations library, which is a very famous library for data augmentations. Albumentations is like the go-to one-stop library for all kinds of augmentation. Apart from this, it supports model conversions. So even though it is trained in PyTorch, it supports the conversion into ONNX, TensorRT for NVIDIA GPUs, OpenVINO for Intel cores, CoreML for Apple devices, and TensorFlow JS and TF Lite for browser and mobile applications. So it supports multiple varieties of model exports, which is very easy for the model to deploy. What sets the library apart from the other repositories are its ease of use. Whether you want to perform training, evaluation, or even prediction, it's just a single command. It supports multiple input types ranging from webcams, videos, folder of images, single image, multiple images, single video, multiple videos, RTSP. So many things it can support actually. So it's very easy to use. If you want to just use a pre-trained model, it's just a single command. Because of its ease of use, it has gained huge community support, and also it's very well documented and regularly updated repositories. So they made so many frequent updates for the pre-trained weights as well as the repository as a whole. And it has gained a lot of community support because of its ease of use. And because of which PyTorch also has started YOLO-V5 models as part of their hub. This makes YOLO-V5 a powerful one-stop solution for the whole object detection and deployment across various platforms. Okay. Now let's dig deeper into the architecture. As we have seen earlier, YOLO-V5 architecture looks like this. It has modified CSP darknet, it has modified the spatial pyramid pooling and also modified the path aggregation network, and it has made some changes in the detection head as well. Let's go into these details one by one. If you go deeper into the architecture, it looks like this. This is the backbone part, which is CSP darknet 53, and this is the neck part, which is path aggregation network. You can see two paths here going in top down and bottom up later, right? This is path aggregation network. And then we have V3 detection head. So it's not exactly the same as YOLO V3 detection head. They have made some changes to the prediction values and target calculations. So we look at those in detail. Now let us look at these blocks one by one. Let's start with the backbone, which is a modified version of CSP darknet 53. So if you remember from our YOLO V4 videos, CSP darknet 53 is actually a modification of darknet 53 with the addition of CSP bottleneck blocks. So what is a CSP bottleneck? CSP bottleneck means cross-stage partial networks. So it's a kind of mechanism. They have added that into darknet 53 and made CSP darknet 53. First, let us look at different types of layers present here. The first thing is convolution. Here convolution means convolution plus batch normalization plus the activation. So the activation is SILU here, which is also nothing but swish. Both are same. Okay. So this is the activation function. How does it work? It's just the multiplication of input with the sigmoid of the input. So this is the sigmoid activation function. Just multiply that with the original input. You will get SILU activation or swish activation. Both are same. Okay. And also the CSP block has been renamed as C3 block. C3 indicates it's a CSP block with 3 convolution layers. That's it. That's why they named it as C3 layer. This is the CSP bottleneck block. We'll come to this in a minute, what exactly is happening here. Apart from these two types of layers, we have spatial pyramid pooling fast, SPPF. And this SPPF implementation looks like this in YOLO-V5. In this, if you look at the layers, there are convolution layers, max pooling layers, and concatenation layers. So in overall, we have 4 types of layers available in the whole backbone. One is convolution, which is a combination of these 3. And second thing is your CSP bottleneck block. And next you have pooling layer and concatenation layers. So these are the layers which are available in the whole backbone part. Now let us look at the CSP bottleneck part. In CSP bottleneck, this green color box is called the bottleneck block. We have 2 paths basically in this CSP. One will be the original path where you go through multiple computations. The second will be the parallel path, which is kind of residual connection where you have only one convolution operation. So the basic idea is you have 2 paths which will give you less computation complexity. At the same time, you will have better gradient flow in the backpropagation. Okay. So this CSP block is introduced to reduce the redundant computation of the features. So one path goes through the whole computation, whereas the other path bypasses it. Okay. If you look carefully, the same input is going for both the paths. But this was not the case for the original CSP block. If you look at the original CSP block, it looks something like this. In the original CSP block, the input is actually divided into half in the channel dimension. So here there are C channels and here C by 2 and C by 2. One path will directly go as a residual connection with only single convolution, and second path will go through multiple blocks. Okay. And finally both of them are concatenated together. But if you see here in YOLO-V5, it is not splitting into halves. The same X goes as input here and same X goes as input here. Both are same. Okay. That's one difference if you look at the original CSP block. And these are simple bottleneck blocks. Bottleneck consists of 2 convolution layers and 1 residual connection. That's it. This star N indicates it can have multiple bottlenecks. Okay. So this green box will be repeated multiple times depending on the number of times you mentioned. Basically in the initial layers, it is only 3 bottlenecks. In the next CSP block, you will have 6 bottlenecks, and after that you will have 9. Like that it will go on increasing. Okay. We will look at the whole architecture in detail again. But this multiplied by N indicates that it can have multiple. It can have repetitive blocks multiple times before it gets concatenated with this. Okay. So that's about the C3 block in YOLO-V5. If you want to understand the CSP bottleneck concept, like why is this bottleneck required, what is the purpose of this CSP block, all that in detail, please watch my videos on YOLO-V4. It's a part 2 video where I explained in detail about the CSP architecture. So next comes the SPPF, Spatial Pyramid Pooling Fast. Everything is fast in YOLO-V5. Okay. Even though it's considered as part of the neck, if you remember in the architecture diagram, I showed this as part of backbone. So don't bother about that. It's just the last part of the backbone or it's the first part of the neck. Okay. However you perceive it. SPP is basically spatial pyramid pooling, right? This is the original SPP. It's not the YOLO-V5 one. In this original SPP, you will pass the input through multiple convolution layers and then you will have the feature maps from the convolution layers. On top of this feature map, you apply the max pooling operation at different kernel sizes. This is a different kernel size, this is a different kernel size, and this is a different kernel size. Suppose this is 3 by 3 and this is maybe 5 by 5 and this is maybe 9 by 9 like that. Or if you go in this direction. So basic idea is to try max pooling at different kernel sizes and then concatenate all of them to get a fixed length representation. Okay. And this will be passed to your detection head. That's the idea. Now, why do we need this in the first place? This actually helps the model to identify the objects at different sizes. Because you are pooling at different resolutions, different filter sizes, you are taking some important features at different scale here and another scale here and another scale here. So that actually helps the model to identify the objects at different scales. Okay. You need not to do multi-scale training here, but in the feature level pooling, you are actually handling that. Now let's see the YOLO-V5 implementation of SPPF. Remember the key idea here is to take filters of multiple sizes. But now in YOLO-V5, they actually used the same filter size, which is 5 by 5. So even here it is 5 by 5, even here it is 5 by 5, and even here it is 5 by 5. Same filter size is being used at all the three max pooling operations. And if you see, these are not parallel. In here, these are actually parallel. Whereas here, the output from the first max pooling goes as input to the second one, and then to the next, and then to the next, like this. First, we will do 5 by 5 convolution. You might get some feature map. And on top of it, you add one more 5 by 5 convolution, a different feature map, and then you do one more like that. So the differences here is, one, it uses the same filter size for max pooling, whereas the original SPP uses different filter sizes for max pooling. And the second thing is, as it is using the same filter size, it is actually sequential in order, and from every step, it actually gets the output for concatenation. Okay. Whereas here, all of them actually happens parallelly and all the features are concatenated together. Okay. So this is a faster implementation because you don't have to worry about different filter sizes and the same filter size goes through multiple operations. So it's faster. So that's all about the SPPF. It's a simple spatial pyramid pooling. Just the implementation, there are few changes. Okay. Now let's come to path aggregation network, which is the neck part. This is how a path aggregation network looks like. Basically, it's an extension of FPN. If you consider till here, it is actually FPN. And this is actually an extension of FPN. We add one more path to that. Okay. We call this module as neck because it actually combines features at different levels to get the best features for the detection heads later. This is the backbone part, which is going in this direction. Now, from there, your FPN comes down like this. And from there, again, your path aggregation network, another branch will go up like this. All combining features at different layers. Okay. This is how path aggregation looks like. If you look at the original FPN, it looks like this. So this is the backbone and this is actually the FPN part where it actually combines the features from different levels and then predicts the boxes and probabilities at those different levels. Okay. The idea here is, if you are going here in the initial layer, usually we have the features which are spatially more prominent. That means you have detections of edges, corners, or some shapes. All these are more prominent in the initial layers. Whereas if you go in this bottom up to the top layers, maybe 50th layer or 100th layer like that, here actually you will have more semantic information, where the information about the categories, the whole object, how it looks like, that interpretation will be more in these layers. Now, for predicting the bounding box or for predicting the category, we need both these information, right? First, to identify the category, we need to understand the semantic information. At the same time, to understand the bounding box prediction, right? The position of the object, we want to understand these finer details. Okay. So both of them are equally important. Now, one is in the initial stage and second thing is in the final stage. How do we combine them? So for combining them, this FPN actually came into picture. You start with the highest semantic feature level and then predict some bounding boxes at that level. After that, you upscale it to the next layer. And from this part, you take the parallel branch and concatenate it, and you will get a different feature, okay, at a different scale. And then you predict the bounding boxes on that scale. After that, you do one more upsampling and then concatenate the corresponding feature map from the backbone. So with this, you are actually combining the top level features with the bottom level features. This top level feature and this bottom level feature, the informations are actually propagating here, and we are getting the information, we are getting the features which are rich in both the things. This is called feature fusion. Okay. Now, path aggregation network is actually an extension on top of the FPN. Instead of only this top-down path, we add one more bottom-up path. First of all, we will see why is it required. So path aggregation network has two paths, one top-down and one bottom-up. So in the top-down pathways, like whatever we have seen in the FPN, the same thing continues. Like you take the top level features which are semantically rich from the deeper layers, and then you propagate them downwards towards the shallow layers where you have edges, corners, shapes, these informations are available. Okay. And you combine both of them together to get finer details. Okay. And these will go to the next stage. Now in the bottom up path, you take the low level features which are coming here. And in fact, the low level features can come like this as well. So there is an inherent path here. This one, and this is a concatenation, and this one and this one, right? This is a path here. So the low level features can come like this also. So it starts with the low level features and then propagate upwards towards the deeper layers. It actually helps preserving the spatial information. Okay, this is very important for detecting the object's position, especially for smaller objects. So these two paths actually work together. This gives the fine details which are very prominent in getting the detections. One major advantage of path aggregation network is these shortcut connections. The one I have shown in red here, this is a shortcut connection. Now, why is it shortcut? If you want to go from here to here, in case of FPN, you have to traverse all the way like this. Whereas now there is a shortcut connection, you can directly go like this. Okay. This shortcut connection not only helps in the forward pass, it also helps in the backward pass because gradients flow will be proper, right? So this is how path aggregation network works. Now in case of YOLO-V5, they actually modified the path aggregation network by adding the CSP blocks. So if you look at this top down and bottom up is actually these paths. Okay, this is like top down path and then this is actually bottom up path. Okay, now only difference is instead of pure convolution layers and upsampling, they have added these C3 blocks. This C3 block, these are actually CSP blocks. So these blocks are added to path aggregation network to make it more faster and compute efficient. Okay, so these three arrows indicates the inputs coming from the backbone. 80 by 80 feature map is one from one path and 40 by 40 is from another path and then 20 by 20 is from another path. Okay, so these are coming from the backbone and they actually go up in this path from top down and then bottom up. And from here you will extract again different feature maps at different levels. And these actually go for detection head. Okay, so it has 3 inputs and 3 outputs. In the original paper, these are actually showing 4 inputs and 4 outputs, right? But in case of YOLO-V5, we have 3 inputs and 3 outputs. Okay, now what is left in the architecture? Detection head, right? This is the detection head used in YOLO-V5. This looks pretty complex, right? So let's break it down. These 3 paths are actually coming from 3 different paths from the path aggregation network. All these 3 paths are having the same computation except their feature map shapes are different. One is 20 by 20, next is 40 by 40 and next is 80 by 80. Apart from these differences, the computations are exactly the same. Okay, So let's have a close look at one of the path. This is the feature map coming from path aggregation network, which is 255 by 40 by 40. First, let us understand this dimension. One is the batch size, and 255 will be the number of channels, and 40 by 40 is the spatial dimension of feature map. First, we are doing the reshape operation, right? In reshape, we are actually changing from 255 to 3 by 85. Okay. Why do we need this 85 number? 85 number is required because we have 80 categories for Coco, and then we have bounding boxes coordinates which are 4 values, and we have one objectness score, total 85 values. And this 3 indicates we have 3 anchor boxes per grid cell. This mechanism is same as in case of YOLO-V3. Okay. So this 255, it is 3 into 85 values. 3 indicates the number of anchors, and the 85 is actually this particular dimension. Now we are just transposing this operation just to make this 85 in the end. That's it. It's just a transpose operation, reshape operation. And we are applying the sigmoid operation to make all the values between 0 and 1. That is happening here. And after that, very interesting thing happens here. It is splitting the total feature map into 3 paths. One goes like this, second one here, and third one here. The first one is regarding the categories. This is regarding the categories. That means you have 81 values, 80 categories and 1 confidence score. Wherever you need the confidence scores, that path is this one, 81 values. Now we are remaining with 4 values. Out of these 4, we have XY coordinates as well as WH coordinates. XY is your center point and WH is the width and height of the box. We need to predict these values now. So these two follows a different type of prediction. Because if you remember in YOLO-V3 or even the first version YOLO-V1 also, we have discussed detail in how these predictions are working. So XY coordinates are actually calculated with respect to the grid cell, whereas this WH values are actually calculated with respect to anchor boxes. Okay. So if you look here, this is the grid cell in which this particular object is falling in. So this grid cell is responsible for predicting this person. Now this XY coordinate is actually calculated with respect to this grid cell points. Okay. Grid cell coordinates. Whereas the width and height is actually calculated with respect to this anchor boxes. Okay. So let us see. These are the equations used for XY prediction, and these are the equations used for WH, width and height prediction. So if you remember in YOLO-V3, these equations are slightly different. In YOLO-V3, the first difference was there is no multiplication by 2 here in both the cases. This is new in YOLO-V5. At the same time, in case of width and height, we were actually using the exponential operation in YOLO-V3. Instead of exponential operation, they replaced it with just squaring, power of 2. Okay. These are the 2 changes they have made from the YOLO-V3 detection head. And these are the equations. This particular path is just an implementation of this equation. And this particular path is an implementation of this equation. That's it. These two are the equations which are implemented here. Let's look at them in detail. So the first thing is, whatever we are getting here, these two values, those are actually Tx and Ty, sigmoid applied on top of them. Okay. Sigmoid of Tx and Ty. These two values are coming from this split operation. Now to that you are multiplying with 2, and after that you are doing some addition operation. What is the addition happening here? Cx and Cy. Cx and Cy are actually the grid cell coordinates. Okay. So we need to add these offset of the grid cell coordinates to the model prediction. And after that we get the bounding box with respect to this grid cell. Okay. At this particular stride. What do you mean by stride? Suppose what is the feature map you are getting here? 40 by 40, right? 40 by 40 is the feature map you are getting here. What is the original resolution of the image? It's 640 by 640. How much it has downscaled comparatively? It has downscaled by 16 times, right? If you divide 640 by 40, you will get 16. So that is what the multiplication by 16 here. So if you see this, this is the multiplication by 16, because after you predicted and added the offset values, you need to scale the boxes to the original image size. That is why you are multiplying with 16 here, because your input shape is 40 by 40. Okay. And after that, this is passed to the concatenation layer. That is about XY coordinates. Similarly, in WH, you are multiplying by 2 in the first place. So here also, whatever you are getting these values, these are actually this one, sigmoid of TW and TH. So this TW and TH are actually the offset values which the model predicted. Now we applied sigmoid on top of it, and after that you are multiplying by 2 in this first step, and then you are squaring them. Okay, this is power 2. You are actually squaring them here. This operation, it is happening here. And after that you are multiplying with the anchor boxes. Okay, here you are multiplying by stride, whereas here you are multiplying by the anchor boxes, because anchor boxes are already defined with respect to your resolution. Okay, so you multiply this with the anchor boxes, and finally you have your final W and H, and from here you have final X and Y. Here you have final W and H, and the categories are actually not disturbed because these are already passed through sigmoid layer, and those can be considered as probability scores. So all three of them will be concatenated together here. Okay, so you might get the doubt like, why do we need to multiply this with 2 in the first place? The other things we understood logically, but why do we need to multiply with 2 in the first place? So this multiplication by 2 is just for improving the training stability. Okay, basically when you multiply these values with 2, you will get slightly bigger range because the input is in the range of 0 and 1, right? After sigmoid, you get the values in this particular range, 0 and 1. If you multiply with 2, this range will be increased from 0 to 2. If you used between 0 and 1, the original values, you are actually confining the bounding box into this one. By multiplying with 2, you are making this box slightly bigger so that it is easier for the model to predict the boxes. Basically, it avoids extremely small values during the training, and it leads to better stability. It will also improve the prediction centers. Okay, what I was saying, the prediction center can go out of this value, right? By multiplying with 2. If you don't multiply, it will be always be inside this grid. Now, if it goes out of the grid, it actually is easier to refine these bounding boxes compared to this smaller bounding box in order to get here. Okay, that's the reason actually it is multiplied by 2. Its the purpose is the possible range of the bounding boxes can be wider, so very small predictions will be actually prevented, so that it will be faster training, and as the box is bigger even from the model prediction itself, the adjustments can be learned faster. Okay, so this is the reason you multiply by 2. So hope you understood this particular step. The input coming is actually the output from the sigmoid, so you have sigmoid of Tx, sigmoid of Ty. After that you are multiplying by 2, and then here after multiplication of 2 you are actually adding the offset values for that grid position, and then you are multiplying with 16, which is our stride of the network, to get the boxes at original resolution. Similarly for width and height, you are getting the sigmoid operation output, and then you are multiplying by 2 for the same reason. Then you are squaring them instead of exponential operation. This is just for the faster operation, that's it. Efficient computation, that's the only thing. Because exponential we were using earlier to avoid negative values, because width and height should not be negative values. Here by squaring that also you will achieve the same thing. So they have replaced the exponential with just the power of 2. That's what it is happening here. And then after that multiply with the anchor boxes. Finally all of these are concatenated together and then reshaped into a common value. So this 3 into 40 by 40, all three of them combined together into 4800. Okay, and this concatenation is actually from the other branches, so just ignore it here. So till here this will be the output of this particular branch, whatever we have seen here. This branch's output is 1 by 4800 by 85. This is the output. So this is how the detection head actually works for this particular branch. Similarly, it happens for all the other branches. So this branch, if you consider, it also has the same operations, multiplied by 2, adding the xy offset values, and then multiplied by 32. Why is it 32 here? Because the feature map size is 20 by 20. 20 by 20 means 640 by 20, which is 32. So this will be the straight multiplication value. We already saw this. And here it is multiplied by 8 because it's already 80 by 80. So 640 by 80 will give you 8. So these 8, 16 and 32, these values are actually depending on your feature map dimension. Whereas the other branch, which is width and height, it's the same operation for all of them. Just these anchor boxes will be different from each other. So this particular feature map will have a different anchor box sizes. This feature map will have a different anchor box sizes. and this path will have different anchor box sizes, because depending on the spatial dimension, the anchor box's definition is different. Now from this feature map you have 1200 by 85. This feature map we already saw 4800 by 85, and from this feature map you got 19200 by 85, because this is a bigger feature map, 80 by 80. All of them are concatenated together to get 25,200 into 85, and this particular tensor will be passed to NMS and post processing for the final bonding boxes. Okay, so all these are clubbed together and passed to NMS and post processing. So this is how the detection head looks like in YOLO-V5. The major differences you see from YOLO-V3 head is multiplication by 2 for the XY and WH. At the same time, in case of WH, instead of exponential operation, they use the squaring operation. That's the only difference. Okay, so that's all. This is the whole YOLO-V5 architecture. It's pretty simple. The concepts used are actually CSP.NET 53, which has CSP bottlenecks. This is like C3 layer, just a small modification, and then modified SPP layer here, which is SPP fast. And after that, you have path aggregation network, which includes your CSP bottlenecks. That's the difference compared to original path aggregation network. And then you have the detection head where the prediction types of X and Y, the computations are slightly different from YOLO-V3. And this will go to your reshaping and NMS operation and post processing to get your final bonding box detections. Okay, so this is the total YOLO-V5 architecture. Now I want to show you the live architecture in Netron. Netron is actually a powerful tool for model visualization. I want to show this architecture how it looks like in Netron. Okay, so as the paper is not released, I went through the source code of YOLO-V5 to understand the architecture, and also I found couple of blocks which are useful for understanding the architecture. Okay, let's see that. Hope you can see my screen properly. So this is Ultralytics repository I cloned into my local, and I created a small notebook to understand the architecture. So I loaded the dataset of Coco and I loaded the models. This is from train.py in Ultralytics YOLO-V5. So I just imported the libraries, I imported the dataset, and then I imported the model just to debug what is available in the model. This is the model function call with configuration, number of channels 3, classes are 80 because it's Coco dataset, and from the hyperparameters I am giving the anchor boxes to the particular device, which device to load. So this definition is actually available in YOLO.py. This is inside models and YOLO.py. So this is the detection model. So it goes to this detection model and it initializes the parameters. Whatever the configuration we gave and the number of channels and all other things, it will actually initialize. This is the definition. So when the model is loaded, this definition is getting printed here. So if you see two convolution layers and one C3 layer, which is CSP bottleneck, and then convolution C3, convolution C3, convolution C3. SPPF, which is spatial pyramid pooling fast, and then simple convolution layer, and upsampling for concatenation, C3 convolution. This from here, from this path, it is actually path aggregation network, all of this. And finally, you go to detect layer. Okay, this is the detection layer. This is the total architecture looking like. So if you directly pass this input X to the model, I'm only taking the first part here. So this is only the first part of the model, first block of the model. That's why it is 0. When I pass through only the first layer, which is only convolution, batch normalization, and SILU, these three operations. So as I was mentioning in earlier, each convolution block represented in the block diagram, it consists of convolution, batch normalization, and SILU. Okay, so the first convolution layer has 32 channels and the filter size is 6 by 6. In YOLO-V4 it was 3 by 3. And when I pass the output here, which is x1 coming from here into the second layer, then I will get this output dimension. Okay, so if you see in the first layer output, the output is reduced to 320 by 320. Original input is 640 by 640. This is the original input. This is changed to 320 by 320 and the number of channels are 32 because the filters are 32 here. Okay, similarly for the second layer I am getting 160 by 160 and number of channels are 64. That's why I am getting 64 channels. Like this you can actually debug and see what are the layers one by one. So this is the first layer, this is the second layer, and this is the third layer, and it goes like this. The third layer is actually C3 block. Okay, in C3 block there are convolutions and then you have bottleneck paths. Okay, so this is the bottleneck path where you have two convolutions and just one residual connection. That's it in the bottleneck. Whereas in the total C3 block, you have one convolution in the beginning. After that, you have bottleneck. After that, you have one more convolution. In the parallel branch, you have the second convolution. So in total, we have 3 convolution layers. And then in the bottleneck, we have 2 more convolution layers. That's from the C3 block. Like this, you can actually print for the whole thing. Now you can visualize this as a graph also. For that, I want to convert into ONNX format, because ONNX format actually gives the trace of the whole model and it gives the connections. If you print the original PyTorch model .pt model, it will not look like a graph. Okay. But if you want to look it like a graph with connections, then you need to convert into ONNX or torch script, where you pass the dummy input and you ask the model for all the connections together, connecting together. Okay. When you pass this dummy input and propagates through the model, then only the connections are established and the whole graph will be formed actually in PyTorch. That's why I'm converting to ONNX format. And after that ONNX format, I want to visualize the output shapes also, not the only layer architecture. I want to see from each layer what is the output shape I'm getting, right? So for that, after I get the ONNX, I'm saving it again with shape inference as this one. This step is required only if you want to visualize what is the output after each stage. If you don't want that, then this is enough. With this, you will get only the architecture definition. What is the convolution layer, channels, filter size, like that. But you will not get the dimension of output from that layer. Then you get this ONNX file, and this is where I'm actually running this. So this is Netron tool. This is like a command line I'm running in Jupyter Notebook. And this is the ONNX file. This is YOLO-V5 large, and the port number you can mention. Otherwise, the default will be 8080. Okay. Now, if you click here, it will actually open the new window. So let me actually run this. Okay. So if you see, it is serving YOLO-V5L. Now, if I click here, it has opened actually, but it's in my different browser. Let me bring it here. Okay. So hope it is visible to you. I'm maximizing it. So this is the input. This is a very good visualization. You can see all the interconnections and all the layers available. Okay. So this is the input, which is 3 by 640 by 640. You have the first convolution layer, convolution and batch normalization, and then you have silu activation. Silu activation is nothing but sigmoid and then multiplied by the original input, right? So this is that multiplication operation. Sigmoid is one input and the second one is the X only, the whatever input coming to sigmoid, the same thing comes here. So this parallel branch actually indicates the silu activation. And then you have one more convolution batch normalization and silu activation. And then you have C3 block. This is the C3 block from here. So I will just zoom out to show you. So this C3 block, one is this residual connection. Okay. So this particular thing is residual connection, which is going here. And apart from that, you have one branch where it goes through the proper computation. Just to show you side by side, I'm bringing that here. Okay. So if you see this parallel branch is actually this particular parallel branch. There is one convolution layer. You will see this in the end when I bring it down. So this is the convolution layer which is available in here. And this particular main branch, main path will have one convolution layer and you will have multiple bottleneck layers, right? Remember this, multiple bottleneck layers. So if you see this branch, this is the first convolution layer. And after that, there are multiple bottlenecks. What is a bottleneck? You have two convolutions and addition, right? So this is one convolution, which is convolution, batch normalization and activation function. Similarly, this is another convolution block and these two have residual connection and these are added together here. So this total block is actually a bottleneck. So this particular green block here, which is a bottleneck, this is actually displayed here. Okay. And then this is the second bottleneck and then this is the third bottleneck. Okay. And finally, the concatenation is happening between both the paths. So this path and this path both are concatenated together and you have one convolution here. And this output goes through the next convolution, which is here in this. Okay. So it goes on like this. Then you have another C3 block, that means two parallel branches again. And this time here also you have bottleneck blocks. So here you have 1, 2, 3, 4, 5, 6. 6 bottleneck blocks here. And parallel branch has one convolution and concatenated together. And then pass it through one more convolution. And then you have again C3 block. Okay. So like this the network continues. In case of YOLO-V5 repository, you will see the definition like this. Okay. This is a YAML file, which is the configuration. The first convolution layer, second convolution layer, third convolution layer, fourth convolution layer, like this. So the third one is actually CSP bottleneck path, and it shows here 3 bottleneck paths. So this 3 indicates the second dimension number of bottlenecks. And later you have 6 bottlenecks and you have 9 bottlenecks. That's what we have seen here. So this also I will minimize. Okay. Initially you have 2 convolution layers, which are these two, and then you have C3 block. In C3 block there are 3 bottleneck connections. So in C3 block, this is the first convolution, and after that you have 3 bottleneck paths. This total is 1 bottleneck, this total is second bottleneck, and this total is third bottleneck. 3 bottlenecks, and after that you have the parallel path, which is convolution and concatenation. After that you have one more convolution and then C3 convolution like this. Finally you have SPPF. So SPPF is actually spatial pyramid pooling fast, right? It has max pooling layers. Let's see where are those layers. Okay, yeah, here it is. So if you see, the output from C3 goes through this one. So output from C3 is still here, till this max multiplication. After this multiplication, you have one convolution layer as part of SPPF. If you look at the block diagram, it looks like this, right? So one convolution layer, and after that you have 3 max pooling layers on top of that. So this is one max pooling, this is second max pooling, and this is third max pooling. And every output is coming from the max pooling and concatenated here. This is exactly like this. And then you have one convolution layer. So starting from this convolution and ending with this convolution, okay, this particular block is actually SPPF, okay. And then later you have path aggregation networks and your detection heads in the end. So if you go till the end, you have detection heads. You can see that 3 parallel paths are there, where one is 80 by 80, second thing is 40 by 40, and next thing is 20 by 20. These paths are there. All 3 of them go through sigmoid function, and then you have split function where you divide into parts. 81 probabilities will be the first path, and then you have the second part, which is for xy. That's why you have multiplication by 2, addition with the offsets. So this addition is actually grid cell offsets. So these are the offsets for different grid cells. These offsets are added to the bounding box predictions and then multiplied by 8. Why is it multiplied by 8? Because this is 80 by 80 feature map. In 80 by 80, you can only multiply by 8 because the dimension has reduced from 640 to 80. Same thing happens in this block and the same thing happens in this block. All of the outputs, like we have seen, are concatenated together, and finally it will give the output from the model. This model output will be post processed in the NMS operation later. Okay. So this is how the whole architecture looks like. It's a very simple architecture. It has only 3 major blocks. Backbone is CSP.NET 53, just a modified version. And same is the case for path aggregation network, modified path aggregation network, modified SPP, spatial pyramid pooling, and also slight modification in the detection head. Okay. But the pattern follows the same as YOLO-V4. Okay. Hope you understood how YOLO-V5 model works. Most of these concepts are covered as part of YOLO-V4 discussion as well. So I did not go too much details. So if you feel that you need to learn more about these individual topics like CSP bottleneck, how it is working, why is it required in the first place, all of these details, you can actually watch my YOLO-V4 series. Okay. I'll share the link in the description below. Thank you.